for our second FRQ, which is from 1998. I was 13. You guys were, not born. All right, so we have the graph of the velocity of a car traveling on a straight road, and we have a table of values also. So for part A, during what intervals of time is the acceleration of the car positive? Well, essentially, A of t is v prime of t, so acceleration is positive when, the derivative of velocity is positive, or when v of t is increasing. So there's a positive slope. So v of t is increasing from 0 all the way up to 35. And decreases a little bit here, so increasing here, and it's also increasing from 45 to 50. For part B, we want the average acceleration of the car over the interval from 0 to 50. So average acceleration is the average rate of change of the velocity, which is just slope. So we'll look at the slope from 0 to 50. So we have the point 0, 0 and the point 50, 72. So the average acceleration, or average rate of change of the velocity, will be v of 50 minus v of 0 over 50 minus 0, which is 72 minus 0 over 50, which is 72 over 50. It's calculus. We don't have to simplify if we don't feel like it. Feet per second squared. Part C. Find one approximation from the acceleration of the car at t equals 40, and we have to show our work. So essentially, our acceleration, which we've talked about, acceleration at 40 is going to be equal to v prime of 40, or the instantaneous velocity at 40. And looking at our graph and our table, we can't find our exact derivative, but we can approximate it with an average rate of change. So an average rate of change, if we look at, we're looking right here, we can approximate this with an average between those 2 points. So essentially a linear approximation. So then we have the 2 points, 35, 81, which is right here. And we know for sure it's 81 by looking at our table. And we have the point 45, 60, which is right here. And again, we're finding one approximation. You could use others, but since 40 is right between 35 and 45, this seems pretty solid as an option. So v prime of 40, which is a of 40, is approximately v of 45 minus v of 35 divided by 45 minus 35, which is 60 minus 81 over 10, which is negative 21 over 10. Negative should make sense because it's definitely decreasing, so the rate of change should be negative. So then we know acceleration at time 40 seconds is approximately negative 2.1 feet per second squared. Part D, we get to use a Riemann sum, using the midpoints of 5 subintervals of equal length, and to explain the meaning. So this is back to originally when we were drawing rectangles. Let's draw rectangles. So let's see. Midpoint. So 5 equal intervals. 50 minus 0 over 5, 10. So we'll go from 0 to 10. This is our midpoint value as far as velocity. So here's our first rectangle. 10 to 20, here's our midpoint value. Draw a cross on either side. 20 to 30, we'll look at 25. 30 to 40, we'll look at 35. It's a terrible line, not very straight, that's all right. And 40 to 50, we'll look at 45. And there's our final rectangle. So now, the integral from 0 to 50 of v of t, our dx for all of them, or the, I guess, horizontal width of all these rectangles, is 10. And then we'll look at the heights. So the height of this first rectangle, we'll look at the point, because it looks like about 10 in the picture, but it's actually 12, plus, for this rectangle here, we're looking at 15. So our height is 30. At 25, for that rectangle, our height is 70. At 35, our height is 81. And at 45, our height is 60. So we end up with 10 times 253, which is 2,530 feet. And this is actually the total distance traveled from 0 to 50 seconds. So keep in mind, the reason we got feet is because if you think of every one of those rectangles, horizontally, that was seconds. Vertically, velocity is feet per second. So when we look at area, we're doing feet per second times second. So the seconds will cancel, and that's why we get feet.